Hello and welcome to this lecture. In this lecture, we are going to look at length of arcs. Okay, we usually deal with length along a straight line. What if you are not walking along a straight line? You are walking along a curved path. Okay, now how do you compute length in that case? Okay, so that's this application. So let's see why it's useful. So for instance, here's a simple thing that all of you have seen. In a racing track, it's usually curved in this fashion. It need not just be people running. It can also be a race car track, or a road, or a railway track. I mean, anything that bends and turns and curves around, you still need to know the distance that's traveled along that curve. Okay, that's the correct distance, isn't it? So you have to be able to find the length of an arc. Okay, so this you can imagine has numerous applications. Anywhere you go, anytime you have a curved object and you have to find the length or anything else, you need to know how to find the length of the arc. So here again integration is your savior, but you have to form the correct integral. You have to form the correct Riemann sum. Okay, so we'll see how to form the correct Riemann sum in length of the arc. Okay, so here is a abstraction of this problem. I have a general f of x versus x. Okay, how do I find the length of this arc when defined by an arbitrary function f of x? Okay, I'm walking. Let's say I'm walking along this path, right? What is the distance I've walked? It's not a straight line, no. How do you find the distance I've walked along this path? Okay, that's the problem, and we'll do that again using Riemann sum. Again, break it up into smaller parts, find this distance in smaller part, and tend to the limit, and you'll get the answer. Okay, so let's try that. Okay, so I'm going to illustrate it with the semicircle. Okay, why? Because the semicircle is very important, and it has captivated people for a long time. So what is the length? What is the perimeter of the semicircle, or what is this length? Right? If you walk along the circle, what is the length? So this is a particular special case of the length of the arc, which is very important and interesting all across science and engineering. So circle is a very important object. It shows up everywhere, and you should know what is the length of the arc of the circle. Basically, if you walk along a semicircle or a circle, what is the length you have walked? Okay, quite often we run around in circles, right? So you should at least know how far you are running if you are running around in circles, right? So that's important. So here is the function f of x is root of 1 minus x squared, right? So this is the function, and I'm plotting it between minus 1 and 1. Okay, of course there is also the other side, but the other side will make it complicated because it won't be a function anymore. So it's just plus minus type thing. So we'll just do root of 1 minus x squared between minus 1 and 1. If I want the full circle, I will just double it, right? So it's okay. So how do I go about finding the length of this arc? So I'm going to divide it up into infinitesimal small delta widths, and then find the width there. Okay, how do I do that? Okay, so here is the important thing. So infinitesimal length of an arc is a little bit more complicated than area. Okay, why? Because I'll show you why. So let's say I start at A and look at a small distance delta away. Okay, I start at A and I go to A plus delta. When I go to from A to A plus delta, this function would have increased by some delta y, isn't it? This function would have increased by some delta y. What is an approximation for the length of the arc? It is actually this hypotenuse. Okay, it is not any rectangle area or something, right? It is not even this length. Okay, this length is different. No, it is actually the hypotenuse between these two. Okay, so I have to take that infinitesimal length. Okay, so that's what complicates things slightly when you do length of arc, right? So it's not just area or rectangle or sum of delta plus delta y. It is this hypotenuse. What is the hypotenuse? Luckily, we have Pythagoras to thank. We know hypotenuse quite easily. So delta y, so before we go to hypotenuse, what is delta y? Let's just look at delta y. The function when x varies from a to a plus delta, function will go from something to delta y, and the delta y is f of a plus delta minus f of a, isn't it? F of a plus delta minus f of a. But now we have our wonderful mean value theorem to thank again. I know that there is a c between a, b. B is actually a plus delta. Change panikiran. So delta y is f of a plus delta minus f of a, and that we know from the mean value theorem is equal to f prime of c times delta for some c in that interval. Okay, so once again we have to thank mean value theorem here to give us a very clear description of delta y. There is some point c between a and a plus delta, so that f prime of c into delta will be delta y. We know that that's true, right? So we know delta y. How do you find the hypotenuse? The infinitesimal length of the arc is the hypotenuse length, which is square root of delta squared plus delta y squared. Now I know delta y is f prime of c square into delta square. I can take delta square common outside and then you have the square root, so delta square will become delta, so you just get square root of 1 plus f prime of c squared times delta outside. Okay. So, infinitesimal length of the arc here, this hypotenuse length, is actually square root of 1 plus f prime of c squared times delta. What is c? C is some point in a and a plus delta as guaranteed by the mean value theorem. Okay, so some point, I don't know what it is. So, this is the formula here, slightly more complicated than area, but nevertheless easy enough to derive. Okay, so how do we put this to use? For a longer length from A to B, we can now do a Riemann sum. Okay, supposing I want arc of f of x. Now, I have gone back to the general f of x. In the previous slide, we had the example as the semicircle. Just to illustrate to you, the semicircle is important. Now, I am going back to the general f of x. I have a general f of x and I want to find the length of the arc from A to B. Okay. Once again, I will use the trick of the Riemann sum. Okay, I will form a Riemann sum which will give me the arc length from A to B using my infinitesimal arc length idea. So, how do I do it? First, I divide AB into n regular intervals of length delta, b minus a by n, my standard trick, right. And here, this is maybe the ith interval, right, of width delta, and in that ith interval, the function would have changed by a value delta y, right. So, that also we have seen before. Now, you pick an xi in the ith interval such that the infinitesimal arc length is square root of 1 plus f prime of xi squared times delta. Now, this is guaranteed by mean value theorem, right. All you have to do is pick this xi such that f prime of xi times delta equals delta y, right. So, that is our choice here, and that is always guaranteed by the mean value theorem. So, once you pick an xi here, I know that my infinitesimal arc length, right, for this ith interval is square root of 1 plus f prime of xi squared delta. How do I form the Riemann sum? Just Rn is just a summation I equals 0 to n minus 1 square root of 1 plus f prime of xi squared delta. Okay. So, this Riemann sum now will start at A, the 0th interval will be near A, then the first interval, second interval, third interval, so on till all the way till the nth interval, which will be near B, right. So, that is how the Riemann sum works, and if you add up all of these things, I will actually get the arc length from A to B, but I have to tend n to infinity, right. I have to tend delta to 0, I have to make the length very, very small, and that is the final result here. So, the arc length from A to B defined by a function f of x has this integration formula, integral A to B under square root 1 plus f prime of x squared dx. Okay. So, notice how integration and Riemann sum enter into so many useful and important calculations that you have to do with functions. Okay. Not just area, even the arc length or perimeter or something like that. Okay. So, this is the formula. How do we put it to use? Here are some examples. Okay, f of x is x from 0 to 5. This is really, really trivial. Let us just write it down. The first problem asks you for x from 0 to 5, right. So, x from 0 to 5 is really trivial. So, you go from 0 to 5. What is this length? You know how to do it very, very easily, but nevertheless, let us use a formula now. 0 to 5, right, A to B, square root of 1 plus f prime. What is f prime? F of x is x, f prime of x is 1, right. So, it is just 1 squared, which is just 1, and then dx. So, we have to just integrate root 2 from 0 to 5, that is 5 root 2. Okay. So, we already know that this length is 5 root 2, this is 5, this is 5, and by Pythagoras you already know it is 5 root 2, but anyway, this gives you the correct formula. Okay, the next one is asking you for x squared from 0 to 5. So, x squared from 0 to 5 will look like this, right. So, it will look like that. Okay, 0, 5 it is not to scale, at 5 it is already gone to 25. Okay. So, it is just really, really high value there. And how do you do the arc length here? So, let us write down the formula here. F of x is x squared, f prime of x is 2x, and then I have to do integral 0 to 5 square root of 1 plus 2x whole squared dx. Okay. So, this is integral 0 to 5 square root of 1 plus 4x squared dx, and I do not know how to do this. Okay. So, this integral will not work out very easily for you. We do not yet know how to do this kind of integration. We can resort to a numerical computation if you want, right. So, before I show you the numerical computation, let us just also deal with the last example here, that is just e power x, and that will from 0 to 5, I will just write down the final answer, e power 2x dx. Okay. So, these two integrals you can try and compute, but the best way to compute it is actually numerical. Let me show you towards the last lecture, I showed you how you can compute integration symbolically using SymPy. Now, it turns out you can also compute integration numerically. Definite integrals you can compute numerically to find their value. Let me once again bring up this Python interface, which is Colab. It's worth learning basic Python. You have to connect. Let me just connect. So, for this purpose, I am going to import something called NumPy and SciPy. Okay, so these two are very important. So, we integrate, we run it. So, we imported that. After you import, let me just go do it in the next set. So now there is a function called, so you have to define a function here. So, I will do that in one step. Okay. The SciPy has something called an integrate function, and I will use a particular type of integrate function called quad. Okay. And quad, you have to first pass a function, and for that we use lambda. Okay, lambda. So, lambda is a function. I think you define it like this: lambda x colon. One of the functions was np.sqrt of it's just refusing to np dot sqrt 1 plus 4 into x, right. So, that is my function, comma 0 comma 5, right. So, this is what I want. I hope this runs. Okay, there you go. So, it is giving me an answer. So this is a way to call the integrate function in SciPy. Lambda x, I have just defined the function here, square root of 1 plus 4x squared, from 0 to 5 integrate. It tells me the answer is 25.874. Pay attention to this number. This is the error. This is telling you that the error has gone down to t power minus 8. There are no other warning messages. So, this is a correct integration. So, this is a way to numerically integrate. I showed you symbolic integration. Maybe we can also try symbolic integration for this. We may get some answer. We will see that later. You can try that in SymPy. What will be the symbolic integration of this? That also is worth it. But numerically, you can compute this very easily. So, the length of the arc x squared from 0 to 5 is roughly 25.874. Okay. And for e power, you will have to do this square root of 1 plus np dot exp of 2 into x, right. So, if you do that, you are going to get 147. This is very accurate, minus 10. So, 147.87695, whatever. That is the area for the length of the arc of e power x from 0 to 5. It is much larger than, longer than x squared arc. Okay. So, that is a quick Python illustration of how to do this. Okay. So, these kind of tools, using Python and Desmos are very important. They quickly give you a feel for what the actual number is and quickly tell you whether you are on the right track or not. Okay. Thank you very much.